Hello, everybody. I'm Mahmoud Salamati. I'm a PhD student at Max Planck Institute for Software Systems, and I'm gonna present you a recent work on decidability of time-bounded reachability problem for continuous time Markov decision processes. This is a joint work with Rupak Majumdar from Max Planck Institute for Software Systems and Sadegh Soudjani from Newcastle University. In real world, there are many situations that we are put in an uncertain environment so that we have to make wise choices in order to achieve certain goals before some deadline pass. Some examples are scheduling for queuing networks or maintenance of multi-component systems or yield management systems. In all these examples, we need to solve finite horizon problems for continuous time models that include stochasticity and non-deterministic choices. Continuous time Markov decision processes, or CTMDPs, they include both stochasticity and non-deterministic choices. And further, as their name suggests, they are continuous time models. Let us describe CTMDP model using an easy example. So this graph shown on the right of this slide corresponds to a CTMDP with 3 states, state 1, state 2, and 3. And being at the state 1, we are equipped with 2 actions, action A and action B. Action A corresponds to solid links, and action B corresponds to d-dashed link. So therefore, set of actions includes, for this very simple example, only 2 actions, A and B. And finally, we have rate function, which assigns to any given state pairs and for any action from set of actions, a non-negative value. So for CTMDP, given a rate function R, if we choose an appropriate action, going from a state I to a state j after time t is computed using this relation. Here one can notice that transition from a state I to a state j can happen at any arbitrary positive time instance. And this is in contrast to discrete time models. For example, going from a state 1 to a state 2, if we take action A, it's possible with this probability after passing time t. Or again, taking action A, we can go to the state 3 with the complement probability written here. Another important concept for CTMDPs is policy. A time positional deterministic policy is a function that for any at any state maps the timeline into set of actions. In this work, we only consider time-bounded policies because we are considering time-bounded problems. And here is the statement for the formal statement for time-bounded reachability problem over CTMDPs. We're given a CTMDP with n plus 1 states, including marked state as good, and the corresponding set of actions and rate function, and also a given positive rational time bound. And we are asked whether there exists a policy with which we can start from an arbitrary state S, and before time B, we can reach to the good state with probability higher than a given threshold denoted by R. And in the literature, there are a couple of works that try to approximate optimal time-bounded reachability probability. And they use techniques such as uniformization. However, the decision problem for time-bounded reachability problem is yet open. In this paper, our main contribution is that we show that time-bounded reachability problem for CTMDPs is decidable subject to Shanwell's conjecture. And the second contribution is that we consider a very famous problem from linear dynamical systems called bounded continuous Skolem problem. And we show that it reduces to checking if the time-bounded reachability problem has a stationary optimal policy. I will first continue with the first item. So for a given instance of time-bounded reachability problem or CTMDP, we call a policy to be optimal if it maximizes time-bounded reachability probability. So this optimal policy can be stationary, meaning that it is time independent. So this diagram shows one example of such a stationary policy. As you can see here, the policy is taking action A throughout the whole time interval between 0 and B. Therefore, it's time independent. Now, taking a stationary policy, analysis over CTMDP will reduce to the ones for the corresponding continuous time Markov chain or CTMC. If we look at time-bounded reachability problem, the version for CTMCs, we will find it quite similar to the one for CTMDP. The main difference is that here there is no policy to play a role. And this makes the problem somewhat easier. It is shown that for CTMCs, we can formulate time-bounded reachability probability as solution to a linear dynamical system that is illustrated here. So here, matrix Q is transition probability matrix for the corresponding CTMC. And also we know that a solution to linear dynamical systems is in the form of exponential polynomials. So here you can see the terms that appear within an exponential polynomial. There exist exponential terms, powers of time, cosine and sine. So this last term can be broken to sine and cosine terms depending on value of this variable. So this time-bounded reachability problem for CTMCs was open until 2000, and that at that time it was proved to be decidable. And surprisingly, the proof for decidability of time-bounded reachability for CTMCs uses tools from transcendental number theory. So as I mentioned before, optimal policy for time-bounded reachability problem for CTMDPs can be stationary, but it can also have multiple switch points. So here is an example of such policy that has two switch points at time points T1 and T2. So switch point is defined as a time point at which the optimal policy takes different actions right before and right after this time point. For example, you can see that at T1 and T2, such thing has happened. Therefore, they are switch points for the optimal policy. Now, the question that arises here is that does the optimal policy have to have infinitely many switch points as illustrated in the figure on the right, or not. And the answer to this question is given by a theorem that states that there exists an optimal policy for the time-bounded reachability problem that has only a finite number of switches. And this is very important piece of information that we will make use of it for giving our decision procedure later. So in particular, we are interested in computing number of switches for the optimal policy. And to that end, we first prove that every switch point of the optimal policy is associated with a non-tangential zero of a specific exponential polynomial. So details can be found in our paper. So here I'm just gonna give you an intuition. Let's assume that Z is an exponential polynomial that corresponds to the optimal policy, to the switch points of optimal policy for CTMDP. And you can see here that this function Z has one tangential zero and two subsequent non-tangential zeros at times t1 and t2. And as this theorem states, the tangential zero has not led into any switch point for the corresponding optimal policy, whereas the two later non-tangential zeros have led into switch points for the optimal policy. So we now we know that switch points of optimal policy, they correspond to non-tangential zeros of certain exponential polynomials. But it should also be mentioned that reasoning about zeros of exponential polynomials is not a trivial task. However, there exists a theorem that assumes Shanou's conjecture and proves decidability of the theory of reals when it's augmented with exponential, sine, and cosine functions over finite intervals. And this Shanou's conjecture mentioned here is a very important and unifying conjecture in transcendental number theory that if true, many results in the transcendental number theory will hold immediately. So one very simple result of this Shanou's conjecture is that if it holds the numbers pi and e, the Euler number will become are algebraically independent over rationals. Now, if we consider this theorem, results of this theorem, we are interested in checking if a given exponential polynomial has a zero within a certain time interval or not. And we find this fairly easy to be encoded in theory of reals augmented with exponential, sine and cosine over finite intervals. So we just need to ask whether there exists a time point which is within the this time interval, and the desired exponential polynomial becomes zero at that time point. However, we are more interested in reasoning about non-tangential zeros of exponential polynomials, and we know that reasoning about non-tangential zeros of exponential polynomials can be created by looking over derivatives of these polynomials. And now one helpful point is that derivatives of exponential polynomials themselves are exponential polynomials, potential different ones. And this means that we can encode checking for existence of non-tangential zeros for exponential polynomials just by considering additional terms over their derivatives. And this also means that we can check for existence of switch points for optimal policy of a given CTMDP in the theory that is stated here. So the theory of reals, when it's augmented with real, with exponential sine and cosine functions over finite intervals. Now let's continue with defining two rather general predicates. The first one holds only if the optimal policy for the given CTMDP has at least k switch points before time b. And the second predicate holds if only if the optimal policy for the given CTMDP before time b has exactly k switches, and furthermore, this inequality holds. Here, y denotes a specific exponential polynomial that corresponds to a sequence of actions that are picked by the optimal policy at times t1 to tk. So because answering to both defined predicates in the previous slide can be expressed by a number of satisfiability questions in theory of reals augmented by real sine, by exponentials, sine and cosine functions. Therefore, we can present our decision procedure by this flowchart. So here, in the left loop, we are trying to compute maximum number of switches of the optimal policy. And to that end, we inductively increase number of switches, and we ask by evaluating this predicate whether the optimal policy has one more switch or not. And once we leave this this loop, we know the maximum number of switches for the optimal policy, and we can feed it into the second predicate, and evaluating it, we can get answer to time-bounded reachability for CTMDP. Therefore, we proved that the time-bounded reachability problem for CTMDPs is decidable, assuming Shannon conjecture. Later, we will consider a related problem, namely to check if time-bounded reachability problem has a stationary optimal policy. And we show that this problem is Skolem hard. So let's continue with this item. If you remember, the very first step of our proposed decision procedure was to check if the optimal policy has at least one switch point or not. And this question mainly is equivalent to this to the statement of problem 2, which asks, given a CTMDP with n+1 states, including marked state as good, and corresponding set of actions and rate function, we want to decide whether there is an optimal stationary policy for the given instance of time-bounded reachability problem. And we already know that answering to the problem 2 is possible by invoking Shannon's conjecture. And the main question is that, is it likely that we can come up with answer to problem 2 without invoking Shanno's conjecture? To answer this question, we've made connection between this problem 2 and a very famous problem from linear dynamical systems called bounded continuous Skolem problem, which asks for a given linear dynamical system, given with described by this set of equations with rational initial conditions and matrices and the positive time bound, whether there exists a time within the interval such that the solution to this linear dynamical system has a non-tangential 0 at that time point. And this problem is has been open for many decades, and only recently it was shown that it is decidable subject to Shanno's conjecture. But the problem itself is quite hard, such that the only decidability result requires Shanno's conjecture. So we proved that given any instance of bounded continuous Skolem problem with an nth order dynamics depicted here, and rational, initial conditions and so on, we can construct a CTMDP with 2n plus 2 states, such that the solution to the dynamic system has a non-tangential 0 within the desired time interval, even only if the optimal policy for the CTMDP and the specific instance of time-bounded reachability is not stationary. And this shows that if we come up with an unconditional decision procedure for checking if time-bounded reachability problem for CTMDPs has an optimal stationary policy or not, we can immediately come up with an unconditional decidability procedure for the bounded continuous Skolem problem as well. So this brings us to the end of this talk. So the main contributions of this work are listed here. So first, we showed that time-bounded reachability problem for CTMDPs is decidable assuming Shanno's conjecture. Second, we showed that whether time-bounded reachability problem has a stationary optimal policy is decidable subject to Shanno's conjecture. And furthermore, we show that this later problem is Skolem hard, and therefore it's not likely to be decided unconditionally. Thanks for your attention, and goodbye.